The scheme that I showed you was a deferred update, also called lazy update. You install the changes when you commit. You have to be careful to read your own values before you look at memory. Committing requires work because you have to install the changes, but avoiding zombies is much easier. Consistency is easier. Direct updates have the advantage that committing is very fast, and committing is presumably the most common outcome of a transaction. So updating things in place has the advantage that the common case is faster, but it's much harder to guarantee consistency. Conflict detection is an interesting set of trade-offs. So in an eager scheme, you detect a conflict before it happens. You say, I'm going to read this data. Oh, wait a second, somebody else has already written that data. What do I do now? Eager conflict detection has the advantage that you can have what's called a contention manager that can apply policies. It can say, well, the oldest transaction always gets priority. That guarantees that some transaction always commits, always eventually commits. You can say the transaction that has done the most work gets priority. You could say the transaction that is going to keep the plane from crashing gets priority. In lazy, it's by the time you get to the end of the transaction, it's too late to make any policy decisions. Often what you see are mixed, where you might treat read-write conflicts differently from write conflicts. And there's a lot of study where you might say, well, when I don't want to keep track of every read because there's too many of them. So there are algorithms called invisible read, software transactional memory systems, and others that have visible read systems. And there's a vigorous debate about how this should be done. So eager detection might abort transactions that would eventually be okay. But lazy detection, if a transaction is a zombie, then it might do a lot of work before it aborts. And so which of these two things happens depends on your workload and your situation. So it's not possible to generalize and say that one is always better than the other. In systems where you can manage conflicts, the question is, how do you manage conflicts? As I mentioned, there are a number of policies. You could say the transaction that's been running for the longest amount of time takes priority. The more important transaction gets priority. One of the most successful one is something that says the oldest transaction gets priority unless it's waiting for something. So you never wait for a transaction that is waiting for another transaction because you don't want to build up queues. So you abort transactions if you're in danger of creating a long queue of waiting transactions. There are many, many possible policies. There has been some work. There's been some theoretical work on competitive ratios and things like that. There's been a lot of empirical work, which mostly shows that some policies work really well for some applications, but not so well for others. But there's no policy that appears to dominate under all circumstances. So that says, for example, that maybe you want an adaptive policy that tries to decide, oh, this is high contention, we should use this policy. This is low contention, we should use a different policy. But this is an area where there's still many open questions. These are different possibilities that you can, that have been studied. There are many others that have not yet been studied. There's an interesting question about I/O. So let's say I want to have a transaction that opens a cash drawer on a bankomat, on an ATM machine. What I don't want is to open the drawer, hand the money to the customer, and then abort the transaction. Because then the bank won't debit its books, but the customer gets the money. And I don't want to debit the books and then not open the drawer because then the customer gets unhappy. And so the problem is that if your transaction is going to have an effect on the outside world and it's speculative, then how do you deal with that? Sometimes you can deal with that by, say, postponing effects until commit. You can say, if this transaction commits, then give the customer the cash. For some applications, that doesn't make sense. One solution is you could say, well, I'm going to allow transactions that are not speculative, what are called irrevocable transactions. Now, an irrevocable transaction is one that cannot and will not ever abort. The problem there is you can only have one of those. So you can have a transaction that runs along speculatively until it tries to do I/O, and then you say, okay, now you're going to become irrevocable. You lose the ability to roll back. But if you have two of them, then they could deadlock. So there can only be one irrevocable transaction at a time, and that's kind of expensive. But it's a solution. Exceptions are an interesting problem. So this is a semantics problem. What do you want to happen if a transaction throws an exception? So here I have a very simple transaction. So I have an atomic block, which is surrounded by a try-catch block. Now, when I create a new node, it throws an out-of-memory exception. Now, nobody expects out-of-memory exceptions, so there's no handler for it. So this exception blasts its way out of the transaction and is caught by the handler. Now, notice that inside the transaction, I incremented I. Now, I throw this exception and I print I. Do I print I equals 0, which means that the transaction was aborted? Or do I print I equals 1, meaning that the transaction was committed? So does throwing an unhandled exception commit a transaction or abort a transaction? Now, the interesting thing is you can argue either way. You can say it should abort the transaction because this wasn't, this was clearly not expected. And if I have an unhandled exception, then something has gone terribly wrong. The least you can do is restore the invariance, restore a consistent state, and then try to handle things. Another approach is to say, well, an atomic block should look like a critical section. And if you throw an exception inside a critical section, it doesn't undo the effects of the critical section. Now, the way the C++ transactional memory standard deals with it is you declare with each exception whether it should abort or commit the transaction, and the default is to abort the transaction. Which is a reasonable compromise, but involves a lot of typing. But there are all kinds of subtle effects, like if a transaction creates an object, aborts, but the exception has a pointer to that object, then what does that mean? And it's probably nothing good. Nested transactions. So if I write a method that has a transaction inside it and is called by another method that has a transaction inside it, then is that okay? Well, clearly it should be okay, because if I want to call my cosine routine and my cosine has a transaction for some reason and I don't know it, then it should still work. So I should not need to know whether there are transactions hidden inside other methods, but this is this involves all kinds of issues. So modularity says you should be able to have transactions. What is the meaning of a nested transaction? So in hardware transactions, they have what they call flat nesting, which says that there's only ever one transaction, but we keep a counter of the number of starts and finishes. And if a nested transaction aborts, the entire thing aborts. The conditional waiting that I described earlier, that's implemented in the Haskell STM system, there's what's called first-class nesting, which says that the child transaction can abort, but it doesn't abort the parent, which is more modular and is more useful, but it's much trickier to implement. It's more expensive because instead of having a single backup version, you need a stack of backup versions. And so the right trade-offs between these are still the subject of some debate. Other issues, so that's mostly programming language issues. So I'm going to close with a kind of a brief survey of other research areas that where people have applied transactional memory to various issues. One of them is locks. This is the lock teleportation that I showed you earlier. There's some other work where some people found a bug in a 20-year-old lock algorithm, this race condition, which could be fixed by putting a hardware transaction around a tricky piece of code. And that turns out that that speeds up it makes the lock correct and it makes it run faster. So the idea here is that locks and transactions can complement one another, and there's not actually all that much work on it. There's only 2 papers here because I couldn't find much other work on this. So looking at how hardware transactions can speed up conventional synchronization is, I think, an area that is open for, that has many open questions. Memory management. The things like malloc and free. There's several issues. There's how do you get malloc and free to work inside transactions? Don't worry if you can't see. The slides will be distributed, so you don't need to worry about reading the titles in real time. But this is kind of a sample. This paper is about how you can use hardware transactions to speed up garbage collectors. This is a similar kind of approach, which says, malloc and free don't work very well with lock-free programs because it's hard to avoid dangling pointers. You can use hardware transactions to alleviate that problem. So transactional memory can be used to improve memory management, both automatic memory management like garbage collection and explicit memory management like malloc and free. There's a lot of work in databases. So a lot of what are called transaction processing databases have the property that when you buy something from Amazon, it goes into a main memory database. You do the transaction and then it gets pushed out onto the disk at the end. Now it turns out that these transactions tend to be very short. You know exactly what they're going to do. You're going to buy a book from Amazon. You can predict their sizes and so on. So this is ideal for hardware transactions. And so there are a number of database structures where the request comes in, you do hardware transactions, or basically hybrid transactions, to update your books, and then asynchronously you push everything off to disk at the back end. And so there have been a number of systems papers that look at different trade-offs and implementations. So if your database is such that it fits inside memory, then the hardware transactions can be useful under the right circumstances. And again, this is the kind of work that is systems work. It's experimental work. The ideas tend to be fairly simple. Validating the ideas tends to require a lot of work. And, these tend to appear in systems conferences and database conferences. One area that I've been working with some of my colleagues are power and energy. So in embedded devices, embedded devices are things like my Fitbit, your GPS, your phones, and so on. Now there are many, many more embedded devices than there are real computers in the world. It's like insects versus mammals. And if you can take an embedded device and they can save a little bit of power, that will do more to help the planet than any operating systems fix you can do, no matter how impressive that is. So we looked at the problem of, are locks or hardware transactions, which is more memory efficient, which is more energy efficient? So locks are not energy efficient because you have to go all the way through the memory hierarchy, and that takes a lot of power. Hardware transactions, when they commit, are efficient because you only go to the L1 cache, and that uses up relatively little power. But if your transaction aborts, then you have to re-execute it. And re-executing takes a lot more power because you're doing everything twice. It's not as bad as you might think because you already have a lot of your caches are still warm. So we have a number of papers where we look at different trade-offs between using hardware transactions and locks in embedded devices. One idea that we used was, it turns out if you lower a voltage on devices, then most of the time these are levels are set fairly conservatively, and so things still work. And then there's a region where you get intermittent small errors that can be detected. And then below that, everything just goes to hell. It's complete to chaos. So if you can lower your voltage until you get to the region where you have transient errors, and then you can use hardware transactions to detect and roll back from transient errors, then you can shave maybe 1/10 of a volt off of your devices. But there are so many devices that even a fraction of a volt improvement is, globally, it's a huge energy savings. And so this is something we're using the speculative nature of hardware transaction memory, not for synchronization, but for recovery. Okay, there's a whole area about what to do about GPUs. So it turns out, you might think that, I initially didn't pay attention to GPUs because I thought, well, why do they need synchronization? They're all embarrassingly parallel, but it turns out that's not true anymore. And so there's a number of papers talking about how to apply hardware transaction memory to GPUs. And GPUs all have weird memory models, and if you think the hardware that I described is hard to use, try programming a GPU sometime. But this is also a very active area where there's a debate about what people want, and then there's a debate about how to implement what people want. And there's no consensus, but there's a lot of possible work to do here. Operating systems, same issue. There's all kinds of synchronization deep in operating system kernels that can be simplified using hardware transactions. Interestingly, many of these papers emphasize the fact that these programs are easier to understand and easier to convince yourself that they're correct. Being operating systems people, they don't prove anything, but they sort of look at it and say, yep, I think it's correct. And it's easier to say that using transactions than using kernel locks. Also, lots and lots of specialized data structures. So it turns out that you cannot take a lock-based data structure and kind of bless it and turn the locks into transactions. That doesn't typically work very well. Why doesn't this work well? Well, so I know somebody who built a machine that runs big Java programs, and that uses their own version of hardware transactional memory for synchronized blocks. Then they discovered that the standard Java concurrent hash table, which is now deprecated, but at the time everyone used it, has an internal counter that is incremented by every operation. Actually, every mutator operation. It turns out nobody ever reads that counter. It's a write-only counter, but that is enough to break any hardware synchronization, because every transaction, even if they touch totally unrelated data, they go to this global variable and they increment it. And so that's evidence that you cannot simply port old software and have it run in a transaction-friendly way. So there's a big research area saying, how can we design data structures in a way that makes transactions work more efficiently? So there's a red-black tree where the first thing you do is, well, the root of the tree is always black, so you write black to the root without looking at it. But that's also terrible, because that means every pair of operations now have a write conflict. So instead, if you read the root and say, if it's black, don't write it, then your program will be much faster. So these are trivial examples, but there are a lot of other interesting things that you can do. There's a lot of work on theory. As I mentioned, Rashid has been a leader in this, and along with other people like Dan Alistar, who I think is here as well. And of course, Michel has done some interesting things here. Hardware architecture. These are papers that describe FPGAs and other kinds of architectures. There's still many interesting questions about how to make transactions work with better architecture. Now that we know what the software needs, we can go back and revisit the architecture. So we don't need to have Intel engineers dictate to us how to do things. We can talk back and say, well, really, if we had this feature, we could make things work much better. Okay, so in my almost penultimate slide, I'll mention that every innovation in computer science goes through something called the Gartner hype cycle. So at the very beginning, somebody invents something. And people look at it and they say, wow, that's just amazing. This is going to bring on world peace. And everyone is all our problems are going to go away. And that's the peak of inflated expectations. Then they look at it again and say, wait a second, all you've done is you've replaced the old problems with new problems. And we don't know how to solve those problems. All you academics are just trying to create work for yourselves. And I feel betrayed and used because you told me that this would solve all my problems and it doesn't. And then there's a reaction, and people write nasty things on Twitter and 4chan and so on. And then gradually the technology, this is true for garbage collection, this is true for virtual memory, this is true for transactional memory. Gradually people pay less attention, and practitioners and scientists and so on work on it, and that's the part where people do gradual improvements, and something goes from being a kind of curiosity, like garbage collection was once considered just total, crazy, crazy stuff that only sandal-wearing vegetarians would ever use, to something that we don't even notice anymore because it's everywhere. And so I think with transactional memory, we're pretty much at the plateau of productivity. It's no longer considered. It's no longer going to save the world, and it's no longer a fake thing. So I'll leave you with a couple of comments. One is that transactions are here to stay for two reasons. One is that they're part of C++, and C++ is here to stay. And the other is it's part of i86 architecture. And i86 architecture, it's like some kind of virus. Once it's never going to go away once it enters that. So between the programming languages and the hardware, this is going to be with us, but we still don't know what it's going to look like. We still don't know exactly how useful it is. It seems to be pretty useful, but things may change. So that's all that I have to say. Be happy to take questions. Yes. So the question was concerned the possible changes to future hardware and what the implications are for transactional memory, if I understood it correctly. Now, it turns out that when you start looking at really massive servers, multi-socket servers, it gets harder and harder to provide a cache coherence. So my friends at Oracle are very worried because they keep putting more and more chips on more and more sockets. They have these huge servers, and they're kind of reaching the limit of what they can do with cache coherence. And by implication, they've kind of reached the limit of what they can do, what they could do with hardware transactions. And I think this implies that eventually they're going to find an alternative to cache coherence, probably some more software-controlled structure. And similarly, there are proposals for hardware transactional memory that are not based on cache coherence. They tend to look a little bit more like database transactions, where you have you have a log, and you can replay things. I didn't really talk about that because that was too much of a departure. But this is also an area where there are some beginning ideas and people have opinions, but it's far from settled. So the impact of new, more scalable architectures on how to do synchronization in general and transactions in particular is still a very open area. Say that again, please. So in the industrial world, I'm not aware of any. There are a number of academic papers that describe small pieces that can be improved. Going from academic papers to something like Linux takes a long time. So to be part of the C++ standard took almost 10 years. To go from an academic paper on hardware transactional memory to Intel was 20 years. So for good reason, industry is very cautious about incorporating new constructs. Remember talking to the Intel people, apparently there are instructions in the i86 architecture that were originally introduced to support hardware garbage collection. And of course, nobody uses these instructions, but they're required to support them generation after generation. So they're very cautious about supporting these things. So the answer is I'm not aware of any industrial operating systems that use any form of transactional memory. But it wouldn't surprise me if eventually something like that would happen. Yes. So the question concerns some. There was an early version of the Haswell chip that had a bug in hardware transactional memory where you could commit a transaction in an inconsistent state. And for that reason, when this bug was discovered, hardware transactional memory was turned off by default in the firmware. And so you could turn it on only if you wanted that. They've since fixed the bug, and all of the current Intel processors support hardware transactional memory in a way that works. So they fixed this bug. They certainly don't think that there were other bugs. Who knows? I think it's there is history of hardware that has these obscure bugs showing up from time to time, and Intel always fixes them. And I think the fact that people discover these bugs means that it's being used, because almost by definition, these hardware bugs are extremely rare. If they were more common, they would have found them. So the fact that somebody found this bug in the transactional memory, in the original transactional memory hardware implementation, implies that somebody was looking at this very carefully. Maybe IBM found the bug, I don't know. But so I think going forward is probably stable. So the question is, why is object-based transactional memory easier than word-based transactional memory. Part of it is you can associate synchronization and recovery machinery with individual objects and not just with uninterpreted memory. And in fact, one of the subjects that will be talked about in the next lecture is how you can take advantage of knowledge about the meaning of the object to get better concurrency in software transactional memory systems. Because if all you see are just uninterpreted bits, then any read-write conflict is fatal. But if you know that this is a hash table and you know that this counter is just a performance counter, then you know you can ignore it. And you can put in type-specific concurrency control, which turns out to be a very powerful mechanism. Yes? So the question is there more work to be done on the specification of a transactional memory? I think the history of work on specification has been, everybody says, we know what transactional memory is, and somebody says, but what about this? And then we say, oh my God, we totally didn't realize that people wanted to do this. So zombies, the work I talked about on zombies was not in the original transactional memory papers because people didn't realize it was important. There are other issues, like if I want to mix transactional and non-transactional operations. There's something called privatization. If I'm working on some data and I want to remove it from the system and work on it outside transactions, can I do that? And it turns out that in early systems you couldn't, things would break. And so I think it would be extremely optimistic to say, oh no, we understand everything. So I think that there is still a lot of work that could be done. Even something as simple as opacity, which I mentioned, is there's one definition of opacity which almost everyone uses, but there are dissidents who claim, oh, here's another definition of opacity that can be implemented more efficiently. Here's another definition of opacity that can, that has nicer properties. So I think there is still a debate going on in those areas. So hardware transactional memory, I think, is also a wide open area because the original implementations of hardware transactional memory were reasonably successful, but everybody has something they want. So as I mentioned earlier, if a transaction can somehow raise a flag saying, I'm running a transaction, please don't touch this data, then the programs, I think, would become much more efficient because a non-transactional program might see this bit and say, okay, I'm going to do something else to avoid crashing this transaction, but there's no way to do that right now. So I think there are certainly some escape mechanisms that could be used to make things more effective. Hardware that is not limited quite as strongly by cache size would be very useful. The hardware transactions in GPUs and other kinds of accelerators is completely unexplored territory. There's five papers in every conference about this, and they disagree about everything. Yes. So I think most STM papers, I think there are one or two that have been formally proved correct. The rest of them, they say, oh, this is obviously correct. And, which is normal for, sometimes it really is obvious. But the techniques for proving, I think it would be interesting to have better techniques for proving things like opacity. There are other properties that I didn't have time to talk about, like privatization and fairly subtle semantic properties. Proving these things is difficult. Proving some of these properties is difficult using existing techniques. You can do it, but it seems like a lot of work. And something that says that here are 4 axioms that if you prove them, you get opacity and privatization and other things would, I think, be of some interest. Mechanical proofs of correctness are always interesting. I think somebody published a, certainly people have done model checking proofs of small system, model checking work on small systems. I think some people at Oracle did a formal proof of a very simple system using a theorem prover. But this is, proving that these things work is of great interest. If you could, if Intel had a better model checker, then they wouldn't have had this bug in their first generation. Yes. So the question concerns whether there are space for escape mechanisms where you could, for example, declare that you don't care about some variables. I think the answer is that you can always find a situation where this would be enormously useful. You can also find a situation where these things could be enormously dangerous. And what you really want is to find a sweet spot where you get most of the useful things, but not a lot of the dangerous things. And there are serious disputes between people in this area who have proposed escape mechanisms, which some people consider as being way too dangerous. And others say, well, they don't go quite far enough because here is a use case where I want to do something else. And so I think finding this balance between something that is so useful we're willing to live with a little bit of danger, and something that is so dangerous that it's not worth doing it, is a very very subtle issue, which is far from being settled. Yes. So you you do have the option of rescheduling your transactions. So when you call xbegin, if you get back a code that says that oh, you were aborted by a timer interrupt, then it could be you were unlucky, and if you try again, you'll succeed. Or it could be that your transaction just is longer than the interrupt cycle, in which case you probably never succeed. So a sensible thing there would be to retry a couple of times. And if it still doesn't work, then to try something else. Now, there is one issue that everyone has with Intel architectures is that the operation codes you get back, you don't know how much to trust them or how much to read into them. And certainly figuring out what these things mean, or giving some kind of specification of what can I rely on given a particular failure code, is something where I think we'd all like to talk to the Intel engineers who do this stuff. Also, debugging transactional code is not easy, because the whole point of a transaction is everything you did was wiped out. And the only thing you get back are these bits. So you can do something like check invariance and then abort explicitly if your if your assertion is violated. But it's extremely slow and painful. And so making this sort of thing less painful would be, I think, a very interesting area of research. Yes. There's no direct support because then you wouldn't really need to have first-class nested transactions, which are not something you want to implement in hardware. So Intel gives you flat nesting. You can go eight deep. So I can do start transaction 8 times, and it's okay. If I try 9 times, then it will abort. For the conditional waiting, what you really want to do is you want to say, here's a checkpoint, rollback here, which you could do in software. So you could use Intel hardware to accelerate this kind of structure, but really it only makes sense to do that in software, not in hardware. Yes. Mm-hmm. So the question had to do with the see if I understood with the ability of being able to predict how long a transaction you can run. Yeah. So the question is, what what are the various things that we can do to make algorithms transaction friendly that are not transaction friendly? So if you look at a lot of concurrent data structures, they consider there's really no cost for reading things that you don't need to read. They're often things like performance counters. A lot of making things transaction friendly is just not doing stuff that will damage a transaction. So things that have no cost in a lock-based system will cause your transaction to abort by introducing read-write conflicts, for example. So things like if you had some way of saying, I'm going to increment this counter and it's a performance counter, don't worry about it, then that would go a long way toward removing some problems. Things like in the red-black tree, before I set this node to black, I'm going to read it and see if it's already black, then don't write it and don't create a write-write conflict where it's not necessary. Things like moving, if you have 2 fields in a data structure, if you move them as separate cache lines so that transactions that read one but not the other don't conflict. So things range all the way from relatively hardware independent things like not writing unnecessarily to very low level things like making sure that things don't share the same cache line. The more you can control your caches, the better off you are. This is true in general, but even if you're not using transactions, then we all know that avoiding false sharing of 2 independent variables on the same cache line, making sure that things are aligned, has a huge effect on the performance of multicores. Again, it's not a good thing that we need to worry about things at this level, but the state of the art is still primitive enough that we have to worry about things at both high and low levels of abstraction simultaneously. And again, in 10 years, I hope I can give this talk without mentioning caches. But in 5 years, I don't think I'll be able to do that. So, so this is a very good question. Intel does not gives you no progress guarantees. They can abort a transaction for any reason whatsoever. And so something using hardware transactions can't really be said to be wait-free or lock-free, because a correct implementation is one that always aborts a transaction. IBM actually does give you some guarantees, but they're very complicated guarantees. So if I were able to dictate to the people who make processors what their next generation should do, I would say I would like to have some kind of guarantee. Now, the nice thing about a guarantee is if you want to do something very simple, you would not need to write a non-transactional backup. Because right now you need two code paths for everything, a transactional code path and a non-transactional code path. And if all you want to do is a compare and swap or a fetch and increment, then it would be nice to not have to include that backup. Your code size would be smaller, your caches would behave better, you would have fewer things to worry about, fewer possibilities for bugs. So I think it's clear that the lack of progress guarantee is an issue. It's an issue that maybe someday will be addressed. I know right now the Intel engineers are not interested in this, because what they say is, well, in practice you do have a progress guarantee, but there are always some very unlikely circumstances where we can't guarantee anything. So our lawyers will not allow us to give you any guarantees at all, because who knows? I don't speak for Intel, by the way. So.